Right, continuing with 23.2, page 346. This is question 6. It reads, what is the height of a cone of radius 6 centimeters that has the same surface area as a hemisphere of radius 6 centimeters? Now, this is a really interesting little scenario. We have just one number, a radius for a cone and the radius for a hemisphere. We've got to work out the height of the cone. It seems like there's just not enough information, but let's just look at it very closely. First of all, let's just draw ourselves a cone. So this is me drawing a cone. Let's make it look a little bit round at the bottom. Obviously that's the circular base of the cone, and I've got a hemisphere as well, which I better do freehand. So there you go. Make it look a bit more like it's got perspective. Awesome bit of artwork, I'm sure you agree. There it is, as a hemisphere, sort of. Now the height of the cone, radius 6 centimeters, has the same surface area. Let me just put a great big equals there. Let's fill in some details that we know. Right, we know the radius is 6, so from there to there I've got radius of 6 centimeters. Same with the hemisphere, I have a radius of 6 centimeters there. Probably doesn't come out very clearly, but never mind. Make that a bit bigger. There you go, 6 centimeters. So that's what I've got. So I have an equal surface area. The word surface area there. Again, you don't need to do this in an exam. This is me just setting it up so I can teach how to do it nicely. Right, and the question says, what is the height of that cone? Right, so let's just have a drop down red here. So I want to know what the height is, so I'm highlighting it in red. And so it's a 90-degree angle there. And there's the height h. We need a couple of formulae. Well, you know the surface area of a cylinder. Actually, forget the cylinder. Surface area of a sphere, rather, is given by the formula 4 pi r squared. Now, this part, therefore, is only a hemisphere, as you can see. So I just complete the sphere so it looks like what it might have been before I chopped it in half with my knife. Therefore, the surface area is going to be, well, of the bottom half, that is, of the curved surface, is going to be 2 pi r squared, because what I've done is just divided that by 2, haven't I? Alright, now that's not the rest of it. If I cut across a sphere like that, I also have an area for this part as well. Now, that is a circular face. Therefore, the area of that is going to be pi r squared. So what I've got is a total surface area of the curved surface and the circular face that's been exposed, and therefore total surface area for that hemisphere is going to be 3 pi r squared. Right? Let's just underline that, because that's going to be relevant in a minute. Now over here, let's begin to set this one up a little bit. Now we know that this cone has a circular surface as well, so that's going to be pi times radius squared. That's happy. Now here, to work out the area of the curved surface, there's something rattling, I don't like it. What is it? Is it me? Anyway, table. Right, anyway, to work out the area of the curved surface, it's going to be pi times radius times the length. Now, the length is the slanted length here, not the height h. Therefore, the total surface area of this cone is going to be pi r squared plus the pi r times the L. Now, I don't have a value for the L, so I'm going to need to work something out as an expression involving h, L and 6. And of course, because of the way I've drawn the triangular arrangement there, we can use Pythagoras to create an expression for L. Now, clearly, L is going to be, or rather L squared is going to be, the height squared, the short side, plus 6 squared, the radius squared, the other short side. Therefore, the L is going to be h squared plus 6 squared square rooted. Right? That's a single expression involving length, the way it links to h, and the radius of 6. So here I go then. Let's begin to create an equation. So I know that the area of the curved surface plus the area of the base equals the surface area of this hemisphere. So let's just put this all together. So I've got pi r L plus pi r squared equals 3 pi r squared. Is that alright? Now, if I take my pi r squareds over next door, and of course I can substitute actual values in here and begin to work things out, but let's not get overcomplicated with numbers and pi's floating around everywhere. If I subtract one of the pi r squareds from next door, I have pi rl equals 2 pi r squared. Why is that? Well, it's 3 pi r squared. Take away the single pi r squared, hence 2 pi r squared. Now, L, we can't work out L. We have an unknown there. We can't do it. But we're asked to work out the height anyway. So let's just go for it, shall we? I can work out the L. Why not? And then feed it back into this. Let's just do that. It's easier, isn't it? So the length is going to be 2 pi r squared divided by pi r. Okay, so straight away we can cancel the pi's if we want to, and we're left with 2r squared divided by radius, which leaves me, if you understand your powers, power of 2, take away power of 1, they subtract, therefore I'm left with just 2 times r. Therefore the curve length is twice the radius. So therefore L equals 2 times 6, because it's the same radius there and there anyway, and therefore that's 12 centimetres. Alright, so let's just do a quick sum there. I'm left with, by substituting L into here, I can say the square root of h squared plus 6 squared equals my length, which is 12. Now, squaring both sides, I have h squared plus, let's call it 36 now, equals 12 squared, in other words 144. H squared is going to be 144, of course take away the 36, better work up here now, 144 take away 36, I worked it out as, I don't know, 108. So h squared equals 108, and therefore the height of the cone itself will be the square root of 108, and that gives me a final answer of 10.4 centimetres, and that's really beautiful. Now the way I worked it out originally, because I did do my notes, I hold it up to the light and confess to you I've done it in a really complicated way. Everything that can be worked out in a long way I did. I just wanted to get it straight in my mind before I went flying off with the video. But look, it's much more elegant what I've done on the video at the moment, because look, instead of working out 4 pi r squared and getting an answer, then dividing by 2 and getting an answer, then working out pi r squared and getting an answer, and then adding it on and getting 3 pi r squared and getting an answer, it's too much. As you can see, I've created a very simple equation here. It's pi rl for the curved surface plus pi r squared for the area of the base equals 3 pi r squared, there it is, for this total surface area of the hemisphere. And that's far more elegant, far neater, far less complicated, and there's less numbers to play around with. So I want to stop there. That's worth a video on its own. It's worth you considering the way you've done that, the way I've done it rather. You can do it any way you want, but it will involve 3 pi r squared one way or the other, the pi rl for the curved surface and the pi r squared for the base anyway. Right, if you arrive at 10.4, there's no way you can fluke that. Let's make it all pretty, just sign it off. I've not done that for a very long time. There you go. And catch you in the next vid.